Hello and welcome. In this problem, a rigid tank is divided into two chambers with a partition in the middle, and one side contains liquid water and another side is complete vacuum. The partition is broken and we are asked to find the final pressure, final temperature, and the exergy destroyed, which is depends on the entropy generation, obviously. Such problems are called free expansion. So it can be considered as a closed process if you take the entire system as your system and consisting of two subsystems. So these kind of closed process problems are covered in chapter 5. So in a closed process problem, a system goes from a beginning to final state, B state to F state. In this case, we have a composite B state and a single F state. Okay, so let's go and launch a suitable test app. Obviously, the system is closed. We follow the generic branch, and this is a case of a mixing process. In this case, liquid water mixing with pure vacuum. Of course, PC model should be our correct model because water can evaporate. In fact, it will. Okay, so let's evaluate the states. H2O is our default, obviously default fluid, and the chamber, one side of the chamber contains water at 200 kPa and 90 degrees Celsius. It should be pure liquid, and it is a mass of 4 kilogram. Notice as soon as you calculate the state, the picture shows that it's pure liquid. State 2 is pure vacuum. Vacuum can be represented by zero pressure and zero mass. However, the volume is supplied, so let's write down the volume of this vacuum equals 10 star volume of chamber 1. So the state is found. Obviously, it will be at absolute 0 Kelvin. As you can see, the picture shows absolute black. And finally, state 3, what we do know about state 3 is that it has mass must be conserved, M1 plus M2. Volume of the tank, the new volume is volume 1 plus volume 2. And we don't know any more information about this state, so let's leave it at that. Go to the process panel and take advantage of the energy equation. So to do so, the beginning state has two subsystems, as you can see. This is the left side is the B state and the right side is the F state. State 1, which is H2O, let's say, is my state 1, and state 2 is vacuum, of course, in this case, but we chose H2O. That's why it's showing H2O, but clearly there is nothing there. And state 3 is all H2O. There is no heat transfer, there is no boundary work because overall the system is not expanding or contracting. If I do a calculate, notice that if I do a calculate, the energy equation will get solved, and in state 3 we should have the energy posted back. Yes, calculate there, we'll find the final answers. Notice that the pressure has been found, temperature has been found, and in the process panel you will see entropy generation rate has been found. And because we know the boundary temperature is given to us to be 25 degrees Celsius, I believe. Okay, so let's put 25 degrees Celsius to be precise. The default is very close to that. So the entropy generation rate is known. Therefore, exergy destroyed can be calculated. Exergy destroyed equals S dot gen 1 times TB1. Oops, so I must have mistaken it. Oh, S gen, it's not S dot gen, I'm sorry. So the variable is S gen 1 and TB, and that should give us the amount of exergy destroyed to be in SI units 2.16 kilojoules.